Okay, so we've had the Simon's model. I'm going to talk about it a little bit more today because it turns out there was there's more you can do, and it turns out it wasn't quite the full deal. So and that took a long time for us to figure out. Anyway, it's because of this course actually, because this is actually kind of the 17th instantiation of this course in various ways, right? Anyway, and to start with, it was just pencil and paper. I just did that sort of thing, and then some code, and you build it up slowly and slowly. And then in Simon's model, if you run the model, I'll tell you what I did. I put it as a problem set, which is a question like you've had, and I'm trying to do the thing, and I'm playing around with it, and so in many models, it turns out the initial conditions don't matter too much, right? And you sort of look for that. It's like you can set up in different ways, some randomness, whatever. And that's going to get wiped out, right? It's just transient, and that's fine. So I kind of bullheadedly try to do that for a while, to just sort of wipe away the initial conditions. But it turns out that it's actually really important. I'll get to the stories there. There's some stickers floating around for those people who want a sticker.
They're gone.
They're gone. All right, I'll source some new stickers. Usually I would have a T-shirt cannon by this point, but it's out of commission, unfortunately. All right. So more stickers. By the way, my wife and I visited the artist, right? So I draw some things. I draw some little things. I'm not great, but I sketched out this idea of a robot years ago. It was totally to make Bongard happy, of course. And then, when the robots come, we can say that we're sort of on your team. Or if it's the octopuses, also on their team, right? Because it's an octopus in a robot suit. Anyway, it's just for fun. But we visited, we've had many of our friends and relatives move to Vermont, basically, through the pandemic. And one pair of them bought a patch of just a forest out near Burke. And we visited them, and they just have a little hut at this point, and they're going to build something on it. But there's nothing there, there's no electricity, there's no running water. They didn't realize there was no electricity until someone who was making a bit of a driveway for them said, "What are you going to do for electricity?" And they pointed to the telephone poles, and they said, no. Anyway, so that's an expensive fix, I suppose. But anyway, that couple, Rob Baboni is the guy he's a graphic artist and I've known him for a long, long time, so we set him up. It's the most fun thing he's done, I suppose, is make all these critters, and we keep doing them. Of course, UVM hates it, so I've had to have meetings with various admin people, and we had one student just appear out of nowhere with like a cape on with a Roboctopus suit on, like for one of these meetings. I'm like, they wanted to like change all our branding, and so it just sort of popped out of nowhere, which was, I don't know if it helped us, but it was funny. Anyway, it's good. Enthusiasm was good. Goggles, the whole thing. Anyway, all right. I wonder with the 17 thing, what would happen if I asked you, what do you think someone else would say? How do you think you would answer that?
7.
Okay.
I've heard that 7 is the most random number. So.
Yeah, between 1 and 10. That's
right.
Yep. No, it's the same thing. 1 and 20. I think there were no 7s actually. Yeah. Maybe there were only 3 or 4 even numbers, which was good. Yeah. Nothing. There was actually nothing between 6 and 10. That's right. But that's a good for sampling, and we'll get this a little bit with networks. Is like, what do you think someone else would think, right? Which can help people estimate things in much better ways. Puts you away from yourself. Or what do you think a random person might think? Weird questions, but yeah. Okay. I'm not going to decry the social physics thing too much today. I'll come back to that. Let me do that. I'll come back to it. All right. So, boo-boo.
I think Tyler started a meeting on Teams. I saw a little notification.
Oh, well, I'm happy to do that. That's amazing. Okay. I'm worried that if I join that, it will explode everything into flames. Okay, the plan has been, I'll record it and I'll put it up. So I'm just don't, honestly, because there are 2 things going on. Sorry. That would require extensive testing, and I just don't think it works. All right. Damn. Ah. Okay, so I'll record this and get it up as soon as I can. All right. First mover advantage. So this is the end of this Richer model. It's this extra piece. I'm just going to go through it somewhat quickly, and I don't know, we had a visualization, I'm not sure if it will work still. So it's going to be a different approach. So we're just going to think about when the nth new flavor comes along, and I know I'm just trying to connect you back. So the nth new flavor appears at some time, and then we want to see how that group grows. So it's an elephant of some new flavor. So we're not going to worry about this too much, right? But the size of the nth group that appears, whenever it appears, and it's going to, depending on rho, right? So there's going to be immediately some group, and if rho is really low, the innovation rate is very low. We're going to have many of where it's going to be replicated. The elephant's going to be the same. And then very rarely, like a whatever rho time scale, we'll get a new one. But even then, that first one's going to have all this benefit, right? Because if you replicate, there's going to be like 1,000 of these and one of this new one. So the chances of being copied are still low. So it turns out it has this is a nice calculation and some work. Your friend the gamma function appears, but basically there's going to be a break. The first elephant that we set it up with is going to have a different. This is the size, the number, if you like. It's going to have a different story than all of the others that come later on. And you see, if you try to put n equals 1 in here, that would be a 0, right? This would fail. So these are just different things. There's a rho to the 1 minus rho in here, right? So that's a different power, and so on. Okay. So what's going to happen? So basically, there's a few factors, but the main one is that there's a 1 over rho, right? So it's rho to the 1, that's just some constant. Here, and then there's a 1 over rho factor that's greater than expected. So if rho is like, 1 in 1,000, then this is going to be 1,000. So it's going to be off by 1,000. So it's a huge difference, right? It's a huge difference. That first mover gets a real benefit. And because it's usually close to 0, right? The first element is the elephant in the room, right? It's going to really dominate, and I'll have some pictures of this. So this really wasn't picked up on for CCUs because if you approach it from Simon's analysis, you get this zip distribution or size distribution, and that's everything essentially, because it is a if you think about like an infinite number of elephants, then that's normalized, right? But there's one that's off by itself that is huge. And so these are the visualizations. This was a paper from now a few years ago. Fletcher Hazelhurst did the work. He was captain of the cross country team. Great kid. And so what's happening here is this is 1, so 0.1, right, dropping down by a factor of 10. So you expect a new group roughly every 10 time steps, every 100, every 1,000, every 10,000. And so the area here represents the number. And so you can see the first mover has done pretty well, right? And then there are these other different flavors of elephants, and then there are lots of these hanging around. So this is this kind of very typical sort of thing we see with zip distributions and parallel size. This is set up as a zip distribution down here. Internally is the flip. This is the size distribution, right? So it's this thing flipped and then differentiated. But over here, the first movers completely dominate, right? If you run the system, they completely dominate. And as I was trying to say before, when I first played around with this, just competition, because I'd never seen I'd only seen analytic work, and I thought, all right, it's a very simple model. Let's sort of should be a fun thing to run as a good little test. And you can see over here that this is completely. I was trying to remove that, right? I thought there's something funny about the initial conditions, like it should kind of wash out. But that was just being stuck thinking about transients and so on. Now the transient there's no transient here. The one that takes off first really dominates. And so you can see it here in the zip distribution. This is the analytical, this is the theoretical fit here. This is from one realization, so you can see it's not quite right. But there's a band here, and that's from theory as well, or from simulation. So this band, I don't know if it's 95%, but this band shows you just how variable the group size can be, right? So this is the first group, second group, this is on a log space. This is the size of them, the number of them. So you can see it's sitting off a little bit, and then it sort of rolls around a little. But this gray thing here shows you just how much, when you run a simulation, how much variation is possible. So this increasingly sits off, and you can see this is on a log scale. This is 3 orders of magnitude, and that's what that is, right? That's 0.001. There's a 10 to the 3, and then this one is 10 to the 4. So this is, you know, vastly dominant. So that's missed in Simon's model, and I think unless he had simulated it or something like that, he was never really going to figure it out. I mean, you could maybe, but using that particular analytic approach, the master equation approach. So you can see, yeah, you can't even see them, right? There are little tiny dots around here, maybe a few, but the chances of them starting is so small. Oh, let's see if the visualization works. I don't know if it will these days. Okay. So there's little guides, right? So you can set the thing, click to play. All right, I'll get rid of this. All right, so we can restart it. So this is a 0.01, and then say a 0.1. So let's restart it. That's going to be.
Why does it change color in the center while it's running? Is that different ones becoming dominant? Or?
No, it's not changing. It's just a color map thing. It's not. There aren't enough colors, so it's a bit funny. Yeah, no, that's fair. Yeah, I don't know why it changes in any particular thing. There are different speeds. There's bike speed. There's rocket speed. Oh, do they both work at the same time? So we could restart this one, and then so with a low one, right? It's possible to get some competitors early on, and then it's going to look like this. Now, of course, in reality, as time goes on, you know, if we're thinking about some real system, you know, this species could get wiped out from disease or whatever, or there's mergers possible. You could add all those kinds of mechanisms. There's another system growing over here with its own thing that comes in and wipes you out. Think about how corporations and so on. Well, but you know, there's a limit. You don't want to get too carried away with trying to make a model of absolutely everything. This tells us a lot straight away. So if we dial it down to which you saw, there's just a few little hops. It's renormalizing, right? When it hits the box, it's just going to renormalize, so it's the same one. And there is a tiny count in there. You can't see it very well. But yeah, just a few. This is a total monopoly situation, right? There's nothing else. I was reading the other day that I don't know if this is really true, but Cornelius Vanderbilt, you know how much money he had relative to everyone else.
It's 1% actually US GDP.
Apparently, yeah, I mean it was like $1 in $20 circulating. He had it in his possession, starting from tugboats. Right?
Railroads.
Yeah, well, railroads to the end of his life,
he
right?
started,
There was more money, right? Another way to make money. Yeah. But that's a rich, that's a system where there's no break, right? I mean, taxation creates if you think about social taxation creates a break on these things, right? And of course, it's from one point of view, this evil communist thing, and from another point, it's like just trying to make the pyramid not quite as, because when the pyramid gets like this and there's just a tower with Cornelius Vanderbilt on the top and the serfs at the bottom, it's, it does make it harder for a system to be, to turn over and be, creative and explore new possibilities. And if it's just, randomness, then we're in trouble as well. But it's this broad interplay between, replication, which is, conserving, and innovation. Yes. Okay. So, this is just, we don't have to worry about it too much, but this is basically 12 hours of madness on a Sunday where I figured this out. That was a very obsessive moment. But anyway, we can do similar sorts of things to what you've seen before and get a kind of a nice little iteration thing. But this again is now we're just thinking about the nth group that arrives and how it will typically grow. And lots of fun things happen with the ratio of beta functions now, because why not? So we can actually get this nice expression. Again, this is for the nth group, and we expect the nth group to typically arrive at whatever it is, t over what am I saying? N over rho kind of thing, yeah. For time. All right. So I just wanted to talk about this, but right. This is that's the typical time that they start. N minus 1 over rho. That's the typical time they start. The initial time for the very first one is 1, and it has a distinct story. And I think, so this is important. We'll talk about some of the history. I mean, I know you see networks now in many classes, but we'll talk about some of the history of some of these things. I think that's more my role there. And Albert, which is the rich get richer model, doesn't quite apply because it's a different mechanism. So horrible business. So we've got an nth group, and this is the probability that, and let's say it's got a size k at some time t. What's the probability that at time t plus tau it replicates, right? So this is just a little specific kind of investigation of how someone or a group that appears, at some point n, it's the nth group, so it's probably n minus 1 over rho. What's its dynamic? And you don't have to worry about all this, blah, 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 this, da, da, da. What's probably that pops up one more, it decays like this, t to the 2 minus rho times k. Okay, so this is a tau, I should say, so tau. Okay. So this is kind of like a little bit like the first return thing, it has some of that feel, but it's, as k increases, this slope, right, so 2 minus rho is a positive number, this is minus a positive number. This, as k increases, this slope gets steeper, right, in a log space. And we know about these things, right, the expected value of this distribution will be infinite if this power is between 1 and 2. If this is between 1 and 2, between 2 and 3, we still have infinite variance, what that mean? But the one we're kind of worried about is, so rho is going to be, right, a little bit less than, it's sort of 0, so this is going to be close to 0, so this is going to be a little bit less than 2. So when k equals 1, we have t to the minus 2 minus rho, which is a little bit less than 2, which means infinite mean. So this is this, and I alluded to the other day, this is I know you don't have to worry about all the math that's here, but this horrible little thing here means that the nth arriving group will have to wait, on average, an infinite amount of time to be replicated. So this is a really bad pyramid scheme, and it's weird that that's inside the guts of this Simon model. But it is sitting there. So of course, we saw it with this little visualization, pop, 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 right? They're growing. But this is, and it looks bad, right? The lower row is, right? It looks bad. There's really that first mover that's dominating everything. But this is absent that first mover part. This is really just, even if rho is small, once you get further into this scheme, right? You're the 1,000th one of these things, you're a new elephant, the time that you expect for your replication will be infinite. Now, there are many things replicating, so something has to be copied, and if you're one that does get copied, and say you get to k equals 2, now you've got 2 in your group, then this decays faster, and you'll expect to get better. So this points to, payola. We'll talk about that more as well, right? If you can pretend that you're a bit bigger at the start, if this was the mechanism that was running the world, then you'd have more of a chance of being, like people would come to you. And this is the great, humans have figured this out, right? They've pretended to be more or bigger than they are forever. Payola is the music thing, right? It used to be that companies would pay radio stations to play the records, and of course then you think everyone's listening, everyone likes this thing, so listen to it. It's now done with all of these things, Instagram, TikTok, whatever. So it looks, you can artificially increase the popularity of something, and then it's going to take off, and all of advertising does the same thing. Okay, so there are other papers like this, Krapinski and Redness. Sid Redness done many, many beautiful things. He's the one, I think I said this the other day, who thinks of his work as like blue collar math, and it's a nice framing. and Mark Newman looking at scientific publications. This is a data, obviously math in as well, but there's some data in here of looking at that. And this connects to the Merton effect, Merton's Matthew effect, right? That if you're the first person to really talk about something. But I'll show you, it's a bit difficult, right? It's the very first, the person who has the first idea, usually not remembered. It's someone who can kind of put it together and have a bit of a story, and maybe there's some luck. Lots of other papers I'm just connecting to these, right? People have worried about this a lot. There's a whole science of science world, as well. And you can worry about what's happening at the start of your network before the preferential attachment takes off. I will say that with this analysis, if you have some network and then the rich get richer thing gets instantiated, then that original network, they all kind of grow and take off collectively. Okay, I'll show you some simulation results because this is not, it doesn't come out of the model. But this is actually, these are group, it sort of seemed like the nth group one, and the n plus one, they're sort of everything would decline nicely. Mathematically, that's true. But the reality is this is group arrival n, and this is how big their sizes are. So it's actually quite varied, right? This is from a simulation, they're quite varied. You can very predictably see that the top one is going to dominate, right? So this is sort of a 2 orders of magnitude situation here. But here's, maybe this is then a median thing through here, but these are ones that never, right, they never replicated. Someone appeared here and they've never got a new friend, they haven't gotten a new friend. And some have done better than expected, some have done worse. So there's a pretty big cone of variation. Oh, I guess, sorry, this is then the time-ordered one, right? If you then rank them. So if we get to this system, they're all jumbled, and now you've got this collection of things, and you say, okay, let's rank them by size and distribution, then that's this line. Looks really good, and it fits the model. But actually, there's a huge amount of variation. This one over here is to do with that probability of replication, so we can leave that a little bit. But this is then the nth group coming along. This is its expected rank, right? So lower, higher ranks mean, of course, it's going down. I should probably turn that upside down. Yeah, it should be upside down. Anyway, these are typical bands, like these are quartiles, this is the median, this would be the 95% confidence interval. So, you're the 100th group, and this is the range of possible sizes you could have at some, or possible ranks, right, going forward in time, because it kind of gets crystallized a little bit. This is, 2 orders of magnitude in variation. This is huge. You could be 30th or 3,000th after some time. So, a lot of luck. This is just absent, trying to game the system, and you can see that it starts to kind of be pretty stable the further you go up, the further you go up. So someone who could be, 100th or 10,000th, and that's within, it's a reasonable expectation. If you're say maybe the 300th that arrives in this pyramid scheme, your fortunes are incredibly variable. So that's not in any of the analysis I've showed you so far, right? There's all the analysis, like, if you're the 7th one and the 23rd one, then the 7th one is going to do better, right? We're going to have this nice, predictable kind of growth. We sort of made these sort of fractional things and so on. Everything is kind of going to grow and grow and grow. But actually, it's hugely varying underneath. So this is one of these things where if you get, you simulate the thing, find the rank, rank them properly, and then check it against your model, it's actually pretty good. But this is the reality. So that can happen, right? You sort of can miss the inside bits. We'll talk about this a bit too. I'll get to it, but looking at real data, that's a hard problem, right? So you've got some growing system, things are getting bigger and bigger and bigger, and you have to try and think, well, did this thing get bigger as sort of as a function of its size in time? It's a hard data set to kind of organize, and it hasn't been done that well. Okay, so this is a funny, this is the last plot for this paper, and the idea here was, let's take every paper that has scale-free networks in the title, which is not the original paper. This is a Barbarazzi-Elwood paper. This is one of the foundational papers we'll talk about. So it has to have this in the title, And then let's see if that obeys a rich get richer thing. And it's very rough, right? Here's the original paper, which again doesn't have the same thing, but it's a couple of orders of magnitude, and if you measure rho, it's kind of roughly sort of fits together, and that's it. But again, this straight line is obviously pretty messy fit in the middle of all that.
Oh, one, I wonder if it's like works for like companies who prefers to market for products. And then two, like say you had some system where like it doesn't like organically produce this, but you have like some metric about that system you could like make that produces this. Like, is that just as valuable, or do those mechanics sort of break?
Hold on. So the second one, you're saying it looks like this, but you want to.
Well, it's like it doesn't like you create some like arbitrary metric for the system that like produces this when you do it a bunch of times. Like, do the mechanics still like function the same way, or is that like you've now abstracted it away where like you can't necessarily relate it?
I mean, there are lots of ways to get to these distributions, I suppose, right? But I mean, what you want to elucidate is both one that you really do find happening in the world, right? So, and that's been a bit of a letdown for these analyses that haven't looked at real data that well, because it is pretty hard to get at. So, because you have to have a lot of bookkeeping, you have to record epochs, and you have to kind of figure out like what was connected to what. It seems to hold up, but it's messy. It's messy. And I will say Simon's model seems to actually really, be roughly what's going on. Things get, you get rewards accrued to your size that you're at now. But you can see this is a really messy thing, right? This is this line of best fit. It sort of fits with the theory, but
Like at 0.5.
this sad one here.
Yeah.
So this is the original paper.
Yeah.
This is like, and this is now paper number, so it's not time. But yeah, there's a paper that follows up that says, scale for networks. This one I think was like some little comment or review or thing, whatever, and no one cared about this.
Yeah.
No, it didn't. They kind of got buried somewhere. I think I used Web of Science, I think, for this instead of Google Scholar. So how do you kind of collect them all? And I think we kind of can now. But yeah, you got to have some zeros. Here are the zeros. It's good. But there are some that have come much later on, these have done incredibly well. They can be like review papers and those sorts of things. So that's something that, at least in the kind of knowledge production thing, that upends pieces, right? And you can sort of see that playing out in different places. There's an idea, lots of people have it. Maybe there's someone that's referred to for a long time, but then it gets cleaned up and repackaged in some way, and then maybe some pieces brought together, and Einstein, for example, he puts a really good finish on some things. It really solves some stuff, but then everything gets kind of just lost, and it's just this. Apparently, one person thought of everything. But for competition in corporations, it's pretty fluky, right? And the old example, and this is from a long time ago, is VHS and Betamax, right? Which were the things you could have at home to watch. You might see them on movies as a joke, but Betamax was the one that was preferred by the film industry as a better quality, right? And so they kind of wanted it, but that's something where it's sort of argued the thing with better quality did not win, and there's this to do with marketing, but it's also just this luck and social construction, because you want to emulate someone around you, right? If they've got this thing, then it's better for you to have the same thing. It's also good if those two people who are your friends have it. And the economists will call it network externalities, which is just, God, they're just bad at words. But that's sort of the idea. Right. So rich get richness is kind of everywhere, right? We love ranking things. So that builds in ways for us to see these lists, right? They're presented to us, or we want them presented to us. Often they're top 10 or top 20. The websites like Yahoo early on and Google, they figured out that 20, and YouTube does as well, 20 is kind of like what people can handle to be thrown in front of you. Like if you search for something, you get 20. It's just a thing. 20 is like, it's not 10, it's 20. So yeah, lots of things. Dogs get rated 13 out of 10. They're pretty forgiving there. And we, of course, will try to rank them in different ways. You see some slightly more sophisticated things. And I said this game, right? Its gameability is huge. Soft puppetry, right? You pretend there's more being talked about. You know, well, I won't say anything other than that. But payola, as I mentioned, John Barron.
He does.
Does anyone know who John Barron was? Who knows who John Barron is? Oh,
He's
is?
Trump's spokesperson, right?
One of
It's
them.
actually
One of
Trump.
them, yeah.
Yeah.
Sort of couple in the 80s and maybe 90s, but he would call in and talk to Forbes or whatever and tell them about his boss, Trump. And everybody's obviously Trump. It's apparently how he got on the billionaire list. It's pretty funny. Anyway, well, I say funny, but anyway, yeah, John Barron. But it's a perfect example of pretending you're bigger than you are, and you know, that's why we have the hype people and all these sorts of things, because it works. Of course, as I'll show you later in the course, it degrades the whole system, as you might expect, but it very reliably makes the system work. This is a funny business now because we're in the Amazon's rankings, or Netflix's rankings. They're opaque. You don't really know, so it becomes harder. Humans, of course, are trying desperately to goose these systems, right? They're trying to figure out ways to. So Amazon, you've got your new book out, and then because you have money, or maybe your questionable publishing house buys 10,000 copies, the first day, and it gets sent to you, and then you send it back or whatever. But that also, that's going to work because they're just counting. And then it's a game, it's a kind of a war game thing, right? So, because then you get up, people who making the ranks will start to see that's happening. Of course, Google was the big ranking thing. When it took off, it was amazing and absolutely trounced every other search engine that was around. Your Excites, your Alta Vistas, the total rubble. Because it worked, actually, was kind of its big feature. But it took a lot longer to game Google. People had to figure out how to do network things and connect things together in networks to pretend that this site in the middle was important. Before, if you wanted people to come to your site because it was about fish, you would just write the word fish 1 billion times in the metadata and hide it. And that was enough because it was all just about the individual thing. But then it became about networks and SVD, I guess, basically. So then you would have these farms, right? You had to then set up a whole bunch of stuff that pointed in ways, and so that was doable, but it took a little while. And then Google reacts, and Google's not as simple as it used to. And of course, then we have this way of, once you get on top of this, you can dial things, right? You can make things spread. And maybe it's enough to just figure out what kinds of messages, if we're talking about Facebook, for example, what kinds of messages spread faster. And of course, lots of testing, lots of trying things out. Pictures of happy dogs and things spread well. That's pretty reliable, but so does people outrage and these sorts of things. So there's the old saying, right, that the truth, basically lies spread faster than the truth. The lies get halfway around the world before the truth has pulled its trousers on. Various things like that, and it's increasingly true. That's social networks, but it's increasingly true if you add a social system on top of an algorithmic structure that amplifies certain things. I mean, how well you've made your social network, your social media network? How well does it spread the truth? And of course that's up to us as well. We have to tell things well and package them well, and the truth is up against a whole infinity of non-truths. That's a problem. So no I'm plugging my cat as a joke, but it's no regramming, right? Instagram doesn't have that. I mean, there's been increasingly more stuff, it's been right now, hasn't it? With the whistleblower and Facebook about Instagram having detrimental effects that Facebook is aware of. It's all very murky and messy, and not responding to it, right? So that the suggestion is harming, in particular, teenage girls, but they're not doing anything about it because there's money and it's all very murky. But they, at least from the start, did not have a regramming feature, right? So that dials down the social wildfire aspect of it. Other things on it are not great, but Twitter, you can just amplify stuff, and we see that all the time. Of course, in Facebook, share. What is that? I've forgotten what this link is. Oh yeah, see, back then, this is 2018. What if a healthier Facebook is just Instagram? because Instagram for a long time really was just kind of pictures and kind of fun and whatever. And but then the political stuff went into it as well, and disinformation went into it. But for a long time, it was a place to put pictures of cats. Okay. Now I realize. Okay, so that was yeah, a lot. Okay. So Herbert Simon sort of talks about it a little bit. He had 1,000 papers, sort of ridiculously productive, and did all sorts of interesting things. And then there's this piece that I'm connecting to here is this battle between Herbert Simon and Benoit Mandelbrot about this, rich get richer thing, like all the phenomena of these parallel size distributions. Mandelbrot's really just going to think about language, as you saw. Simon was talking about everything: cities, species, and again language, and thinking that there's a bigger story here. But they have some amusing stuff I'll show you. Oh my gosh, we'll do it. Is Kitty there? Kitty's there. Okay. So this is academics having a fight. It's pretty funny.
How many bottle sets did you have to buy to be able to spell everything?
Well, we do have the one, and then we do have one, and then we have there's the 5x5 my wife bought, which is just an abomination against God. I think is what that's called. I meant to show this the other day. Let me. Oh, that's fun. I'm not. That's a secret. I'm not allowed to show you that. Did that feel dangerously bad? Here's the boggle section. There's just a few boggles in here. Yeah, one day I could spend a whole semester explaining my directory structure. So I used a big boggle for this one. I didn't show it. I gave a talk on Friday. So, I want to see if this works. But I forgot to show it. I spent like 20 minutes making it. Sorry, what was the question about this important thing we're talking about?
Do you use these like in your presentations and so on? And I guess I just got my answer. You try to, but you forget.
No, yeah. I mean, there are tarot cards, and I just don't explain them. It's just, I might just say that. It's like, I don't know what the. Because I know it's not like, you get. Anyway, I just put things in there and pretend I don't know why it's there. Depends on the audience, right? If you've got your traditional professors, they're all. Academia is very conservative. It's very, very conservative, and they hate this. What's that?
The dream of efficient language. That's a good card.
Yeah. So the dream. So let's inspect that tarot card today. So this is the and of and right. These are the big ones. So they're representing their kind of. This is the zip distribution. It's a machine. It's all sorted out. Instead of a crazy, messy, but that's the thing with language. It is a bit of a mixture of really clean algorithmic kind of structure and then just total madness, right? And I just want to sort of shout out to the French for invading England in 1000 whatever, and helping to create the ridiculous English language. Thankfully, England is basically not at this point, but they did give us a fun language, and that gives you Monty Python. Basically, the absurdity of the language. I think. Look, people are funny in every language, of course, but I do think they had a bit of a kind of a good thing to play with. Anyway, yeah, the dream of efficient language. So because this is now going to be like, it's optimal, right? So Simon's kind of approach is like, it's kind of a mess. And again, we saw that even there's the analytic stuff says, it produces this beautiful zips thing. But in fact, if you actually run the model, it's like, it's kind of messy, and on average, it's doing that kind of thing. So it is a much more random looking output than you would ever kind of realize, I think, when you just did the analysis. So that's a good basic thing, right? Randomness gives us order. And of course, when I said there is randomness, but then there's this, really strong piece in there that's really, the mechanic of replicate, like copying something. That's a very, faithfully copying something. That's a very, solid. It's not just total madness, right? There's something that's happening inside this randomness that's really structured. But it's not saying, the model never says, we're trying to make the best language or the best set of cities or the best whatever. We're just, it's just randomly, it's just copying things. So Mandelbrot, like to call himself, he's a very odd fellow, but almond bread, he would sometimes mention that. Danforth had some story of him leaving him messages years ago on the phone, and he'd be like, Mandelbrot, almond bread, at the end. But an odd character. I think he won a Nobel Prize. He did not go on. But that's what a lot of this happens. Okay, so Mandelbrot said very famous thing, and mathematicians were put on their doors for years to try and entice people into their worlds, and then not actually talk about that. So it was a bit of a Okay, so Zipf's law through optimization, language is efficient, and over time it will become efficient. We've seen, as I said, some evidence of that, like the regularization of past tenses. But you also want to, this is not unreasonable. You want to communicate, a lot of information. Of course, if you have a friend who doesn't do this, or a human who doesn't do this, well, it's infuriating, right? This is for as little cost, and then you have your other friend who's like,
Henry James.
I mean, get an editor, right? But then you've got your pal who just says, whatever. Like this, just dude can mean a million things, right? Dude. It's disgusting. It's awesome. It's really kind of casual. So very little cost there for the broad speaker. Okay, so we need some then measures of information and average cost, and so this is. That's the game, and he's going to contrive. We'll go through Mandelbrot's approach, which is, this paper, which is very well cited. It's sitting in a book actually. It's a chapter in a book, like a collection, not his book, but a collection. So then the claim is language is going to try to get to maximizing some balance. So this is one way to do it. It's h divided by c, right? So you're trying to, if you maximize this thing, then you must be increasing this relative to this. It doesn't really have to be this form. It could be h minus something times c, but that, how would you, what's the something? So this was sort of a rough way to try and get those balances to work. You can minimize the thing underneath, right? So, this is a recurring, right? There's some randomness, there's some madness that's going on when systems evolve. You come around the corner and get eaten by a thing, and you're a very disappointed qual or whatever. But then there's regular patterns, and this great kind of, what am I going to say? I think there's evidence that there's kind of an equilibrium of risk in some systems, and we'll start to see this in the next pieces that come after this: highly optimized tolerance, and where to put all your coffee shops in your hospitals, those kinds of things. There's sort of what I would call equally partitioning of risk. It's something I've thought about for many, many years, trying to write papers on it. Okay, that's going to be the plan. We're going to work through it, but this is just something to sort of chew on, and these big stories like optimization versus algorithms just doing things. And by algorithms, I mean life. I mean everything, right? They're just they're trying to do this stuff, and then they run into another algorithm that's trying to do something else. And again, by algorithm, I could mean a cat and a squirrel. Okay, so Mandelbrot versus something. This is very enjoyable. So I don't really. Has anyone ever seen this? Highlander?
No, yeah.
Maybe.
Yeah, it's been a while.
So it's the '80s, and it's a great movie. But it's referenced still. There can be only one. You'll see that kind of pop up in different places. It's becoming, of course, a further distant memory.
There was a TV series.
It's a TV series.
Yeah.
Yeah. It's amazing. Let me just set up the premise. So there are these. It's basically around some Connor MacLeod, who's a Scottish Highlander in one of the 1300s. who discovers he's immortal, right? And then there's, of course, it's a good story, right? The actor is French, trying to speak in a Scottish accent. Sean Connery is in it, trying to be a Spaniard who was an ancient Egyptian. So of course, and his accent is, he never changed his accent. Like Hunt for Red October, he's just trying to be Russian. It's just Sean Connery, ski. And anyway, so it's it's sort of famous for a lot of things. But one of them is that Queen, the soundtrack is Queen. It's fantastic, absolutely fantastic. The whole thing, not just a few songs. Anyway, so things there should be only one of his theory right in the end when you sort out. And to your point, Highlander films, there should have been only one because they kind of finish it with, you have to fight all the other immortals, and then when you win, I don't know, at the end you sort of have some special abilities. But then they kind of rebooted it and said there were aliens who came from another planet, and anyway, really, really wildly insane. One of the strangest set of sequels. Anyway, but it's a kind of magic is the thing. Anyway, there can be only one as sort of the pieces. We'll watch the trailer for a little bit, not too long. Right, that's enough. So the quickening, right? This is when you take out one of the others, you get this power. There were jokes on Stephen Colbert years ago, and Lou Dobbs lost his job, and he tried to absorb his audience. Anyway, so Mandelbrot versus Simon, right? So here's the history of this. So Mandelbrot, I'm talking about in the second case here, but this was the sort of first paper. And so Zip has published this book in 1949. Of course, people have thought about this for a while, but Zip has this kind of magnum opus appear. So again, with the titles, informational theory, fair enough. And of course, information theory is new, right? It's the late 40s for Shannon. Right? This is a totally new thing as well. So there's a lot happening here. This is structure of language, so it's about languages. This terrible, just unbelievably awful thing. And then Mandelbrot. So this is 59. So this is not tweets, right? This is some specs. 53, 55, 59. A note on a class of skew distribution functions, analysis and critique of a paper by. So he calls him out. The name. Simon, 1960. Some further notes on a class. It's going to stick with the title. It's a good title. It's a good title. But of course, he's saying Simon is Mandelbrot is upset about Mandelbrot. Final note on a class of it's like the baseball bat, and on a class of skew distribution functions. Again, analysis and critique. Reply now it's like now we're engaged. Postscriptum to this is 61. I think they managed to kind of speed up a little bit. Reply to his postscriptum. And then there are these comments like this. This is Mandelbrot, stated in detail, and he's calling it now the Pareto-Yule zip distribution. Let's name everyone. Objections are quite valid.
Is that just the zip distribution, or is it something else?
No, it's just the zip distribution. Yeah, it's just everyone's a champion, so we're gonna name famous people. So in a sense, it's all wrong. Yeah. Okay. So most of Simon's reply was irrelevant. New set of objections, like his early objections, these were invalid. It's just these people are just tearing at each other with the swords of their brains. Okay, it's pretty funny. Okay, all right, that's from the early good part of SpongeBob. It could be this as well.
One man leads, 2 men enter. One.
That was filmed in Australia, of course. That's the third Mad Max film. Okay, so yeah, 2 theories enter, 1 theory leaves. All right, so let's talk about how this works. So language is going to, in his model, it's going to have n words, which I'm saying is tricky, but they're going to be there's sort of a dictionary of words. Ith word is going to appear with probably a piece of I, and then this is sort of the weird thing about information theory about Shannon's entropy is, it does what it does, right? Which is to say you're going to send these symbols, from one end of a channel to another, right? So there's a sender and a receiver. So it's very much, you know, a thing about talking. But the assumption is that they're going to be in some different rates, right? So for example, the word the, you know, 4 in every 100 might be the. But apart from that, there's no structure. Apart from that, the assumption is complete randomness. So it will actually be, you're assuming what's the worst it could be. There's no other way to kind of contend with that randomness of order. But basically, what you're going to say is the word the, if I'm going to encode it and try to like sneak it through this communication channel, then I should have a short code for that because I'm going to use it so much. And the rare ones, really rare ones, you know, I'm going to have a much longer code. And the person at the other end or the thing at the robot at the other end is going to have a code book, right? So you're both going to have these code books and they're going to decode at the other end. It'll take longer to look up a rare word because it's going to have a longer code, but that's okay because it's rare. So in Mandelbrot's conception, actually the composition of letters matters, which is fair enough, right? Because length of word will matter. So it'll be different with a character-based language. Then you'd have to think about like how easy is it to, how elaborate is the character and how easy is it for you to decode or construct. And so we'll have an alphabet with M letters, so it's very much, I mean, you know, the alphabet was contagious, right? So when that took off from the, kind of in the Middle East, it would spread everywhere, according to Glick. And then words are going to be ordered by length, the shortest first. This is also something that's not really, Jake Williams worked on this from our group in this course from years ago. Word length. I don't think it's that well sorted out. But if you think like Morse code, you know, like you want the same thing. Wow, that's for letters. You want the most common letters to have short codes. Fair enough. Scrabble's a zip distribution kind of story, right? That's was from the, I don't remember offhand the fellow who invented it in his 1930s, I think, took the front page of the I think it was in Brooklyn, took the front page of the New York Times and counted up all the letters. Like how many times, did a little frequency distribution thing, and that's why there were 11 or 12 E's, for example. Okay, and of course then they have scores attached to it. So we're going to do this. So word cost is simply going to be the length of a word. So that's an easy, you know, of course this is building a model. This is we're trying to think about how do you construct a, you know, like had a good idea about optimization, fine, let's do it. So how do we do it? And you may, you know, of course we can critique this strongly, and we kind of do it. So word length didn't matter in Simon's model, not that, you know, and of course Simon's model doesn't show you how to write a book or anything like that. Simon's model might be a little bit better for the growth of language from nothing, right? You start with book, you know, and then you've got another word that isn't book, you know, you just kind of slowly get utterances together, different to telling a story, like the growth of a word. Okay, so real words, of course, don't use all letter sequences, so that's going to be part of this. This is just going to allow every permutation. You have M letters in the alphabet, and then a two-letter word could be, you know, M times M possibilities. So in Scrabble, gotta go to Scrabble again. Depends on the rule book, but I think it's like about 100 two-letter words.
112.
Yeah. So it depends. Yeah. Whether Tsar and Key are in there. You know, like there's international rules. There's American. There's decent people rules.
HM and
Oof.
MM.
Sorry, hurt me with that. HM and what's the other one?
MM. Yeah. Scrabble's really just.
So it's the Scrabble people are pushing for this, right? That's the problem. I think. Yeah. Tsar was a good one, and QI also very good. Is that both of those for some nasty behaviors? Best thing about Scrabble, right? Some of the top 10 players are not English speakers, right? Like they're not, because it's just a game. You don't have to know what anything means. Okay. So that's a bit of a problem. Yeah. So instead of 26 times 26, right? We're about 10, more like 10 times 10. So, you know, maybe it's roughly right. So even if we're not using them all, you know, we're using some fraction, it's roughly okay. words can be sort of so you could encode them this way, right? So you could say, okay, here's my zip distribution for things, and I'm going to make the first one have, right? And of course, that's, we turn them into bits or something like that. Okay. So just a little bit about entropy, just a very rough thing, because you have to. There are different ways to approach it. There's Shannon's original paper, which is this sort of thing. It seems remote. It's worth reading. It's 55 pages. It's quite a long object. It was a Bell Labs piece. But this work that we have that's going to appear tonight on the archive is about meaning, and kind of one of the things that it talks about is right at the end is Shannon's information theory. This gigantic thing. But he's careful to point out, I think in the second paragraph, it's not about meaning, right? It's not measuring. So we're conveying words, but some, which of course are, rich with meaning, but it's a bit separate from that. This is a mechanical engineering method. So here are our words, right? So our words are just going to be 1, 1, 0, 1, 1. This is the simplest thing we could do. And then there's sort of a space character as well. So you have 3 characters, right? You're sending these things. So this would be the word, it'd be ideal to make this the and of and. The word squirrel is going to be way down here with maybe 23 things. Unless you're like cat, and then it will be pretty much at the top. Okay. I do think there's data now on meowing sounds. So someone did a bunch of work on this. Did you see this? It's like someone trying to. It's a data set. There's a data set on cat noises.
Oh, cat noises.
It's like whether they're distressed or happy or whatever, and so it's like a whole thing. You could do SVD on that.
There's also on chicken noises.
Meows geometrics. Yes. I think if a deep learning thing could do anything, just like figure out that animal language stuff, which we've been for a long time happy to say is like, no, they don't say anything. It's just. Is that where the word barbarism comes from? Baba, like, wasn't that because it was like that was a mocking of the sound of these people that we can't understand? Right. It was about their language.
Yeah.
I could look it up, but I'll just say it. But if you agree, then what? But and then it's because barbarian is Conan, right? You think it's going to be something about like the chopping people off thing, but it's actually just about the Conan's way of speaking. Actually, I guess it's pretty accurate. All right, so let's see. So word lengths. So these are the lengths of the words. This is just the number of bits. Yeah, and then this is just a little gadget here. It's log base 2 of I. Just noting that it's not right, but these are roughly it grows logarithmically. This is just how this is going to work, and it's exactly right. So the 2kth word, if you went out that far, would be k plus 1. So for example, the 2 to the power of 3 is the 8th word, and that's 3 plus 1. Right? 2 to the power of 2, 2 plus 1. 2 to the power of 0, 0 plus 1. Okay, so we can, right. So we could kind of express it in this way. And so then the word length of the ith word is roughly going to be this 1 plus log 2i. That's it. It's going to grow the logarithm. And if we have m letters, then we're going to have some modification here to make it more basic. So instead of 1s and 0s, it's A, B, C's, and we've got this weird thing. And the forces of optimization for language, they're very real, right? And the grammarians is just terrible humans who say, you're only right, you're not allowed to split an infinitive because Latin infinitives were, single objects, so there's no way you could put something in. But to boldly go is much better than to go boldly.
I'm like a little bit worried about this optimization thing because, like, I don't know that it seems like we explicitly don't try to optimize like the amount of information for the lowest cost because, like, if you think about someone doing that, you'd think they were being rude.
Right.
They'd be very aggressive, right? So,
right.
sort of. I don't know, it feels a little weird.
So Mandelbrot is the person thinking this up, and it's very mechanical and whatever, and I think you're totally right. And what we're going to see is it's an idea. It doesn't really hold up, but it also optimization does appear in some other pieces later on, and it's similar. And so it's going to be a Lagrange multiplier setup for fans of that sort of thing. So it's going to recur a couple of times in a different way. So there's some nice thread there. But for language, yeah, language is. You're also trying to optimize a whole bunch of things, right? Exactly, like you say, that they'll be your friend at the end of the day.
It's just like the complete opposite of like Shannon Nyquist. Like the whole point of that is like how concise can we be without losing anything versus like I don't know. I guess
Well, that's interesting. Okay, yeah. I mean, so this is saying that here's a language, and we observe that here are these. It's inhomogeneous, right? In usage, quite strongly. This is parallel size distribution. And then we just drop everything away and say, well, these words. Let's say the words are going to go down this channel randomly. If that's true, what's the best way to encode them with a bit string or an alphabet sort of string, such that it's the smallest amount of burden on the channel. So they're trying to sort of have everything, but right, what's broken, of course, is the structures between words. And optimization, sorry, I should say this, compression schemes do actually really try to capitalize on lots of structures, right? And it's interesting to think about. I don't have it in here, but that's a whole, like LWZ and so on, they do capitalize on.
Well, the linguistic oddity of headlines is the result of compression.
Yeah. Like the music, song titles and so on. They're actually incredibly rich objects, right? But they don't have a lot of extra guff in them. Yeah. So is that?
I was just gonna say, I think Mandelbrot, if we're going to follow this thinking, we should all just communicate in poetry now. All the meaning, less of the words. You got it.
Well, so you're right, but the decoding is hard, right? Because it's like.
But that's not on me. That's on you. You know? let the
And
let
then,
the audience
so
all
that's
know.
the ideal poet. That's good. That's good.
Well,
Yeah.
I saw.
I was just writing about a fence post, but you thought it was about the end of civilization.
Exactly.
There's a similar thing with like I saw some paper and I was trying to like compare it was either like titles to abstracts of
Okay.
papers and being like how can we like get the most accurate abstract from the title.
To make.
Or it was either like the abstract of the paper. It was like one of those.
Oh yeah. Well, there's a lot of work that's done on synopsis kind of stuff, like automatically compressing things and so on. I know Catherine's looking at some of this is somewhat impressive, it seems, but just the very fact that you might get a coherent set of sentences is enough to kind of trap you a little bit. You're like, but whether it's really, then you have to go and read the whole thing to make sure it's really true. So that's but black boxes are doing that a lot. It is definitely a danger. I mean, who knows? Like if this thing is compressing this information into this little story. Humans do it in weird ways too, of course. But if that becomes a predominant thing, it's unclear.
Has anybody done like a version of this but using like Grice's maxims? Because like if there was a good way to sort of represent that with mathematical formula, I feel like that might be a lot more. I feel a lot better about starting with that for a language.
All right. Well, we can talk about it. I don't know. I mean, there's a lot done. I'm trying to give you. I guess this is sort of historical roots ones. And maybe sure. That's the thing. Someone possibly has done that. I haven't seen anything that's like, Chomsky said this, and here is, an optimizer. Like, I don't know if someone must have done that too. But whether those models really, if they become kind of fun applied math things in a lot of cases. There's a lot of physics models like that. Language is interesting, citations 1 through 20. Here we construct it has an interesting principle, which is a fun exercise. All right. Okay, so we've got this idea, and the critiques are very reasonable. It's also useful to think of when this was done. Information theory, this concept is pretty new. There's also this sort of observation that all these distributions have these heavy tails is relatively new. This is in this 53 for Mandelbrot. Like the fractal thing for him is in the 60s, really in the 70s. Interesting thing about the fractal stuff, there are of course little mathematical things that give you like the Mandelbrot set and you can play with them. But for physical fractals, which really are everywhere, the mechanisms that give rise to them, they're less well elucidated. And that was a gaping hole for a long, long time. It's like, oh, I just described another fractal, I measured it, it's got a fractal dimension of 2.3, it's the insides of a frog, like blah, 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 like, published it over here. But the story of why that comes about hasn't been really figured out.
The same is true with cellular automata. Finding something that does that is different than finding a mechanism.
Yeah, exactly, right. So you can make imitative things, and that can be useful, but you don't want to mistake that for reality. Yeah.
Was Mandelbrot focusing specifically on spoken or written language, or was it just in general? Because it seems like this is like more written if we're counting letters, and spoken would be like counting phonemes.
Yeah. No, it's a written thing, and then I guess the extension to speaking will be that that's somewhat proximal to, a longer word takes a longer.
Right. Yeah, they're definitely correlated.
Yeah. And if you sort of look and like I think sometimes of like English place names where they've left basically all the word, right? It's like old, it's Worcestershire or something like that. Like and it's sort of funny to come to the U.S. and see some words like I think like Warwick, right? Like there's a W in there, but like why not? Just why say it? And I think that's part of like you're saying this more and more and more. Like you make it true. Like Emma, that's like I am going to. That's 4 words down to like a 4-letter word because it's a pretty good. You use it a lot, right? Or people use it a lot. So it's like that just became Emma. So you get these like parts of the language where people use this little structure a lot, and then LOL.
Well, it's sort of like there's 2 levels of words. There's what we actually call words, and there's phrases that are functionally words.
Yes.
And that's really
no one does a good job with that.
Is those, and then there's the combinations of those.
So we have n-grams, and people talk about them, and we've done work where we've tried to break up language into meaningful pieces. Like New York City shouldn't be New York and City. That's ridiculous. Obviously a semantic object.
Mm-hmm.
But
Syntax trees
it's a real problem. Yes?
To defend linguists, syntax trees do that.
Yeah.
Not perfectly, but like they're
But it's,
with their
no, absolutely. People have tried, but it is hard to do like in a way that you would, it's hard to do in a big automatic way that you would really like to do.
Yeah, I mean we have like parsing that does that, that tries to make trees. But I mean all that stuff is kind of hit or miss, like
That's what it is.
all.
Yeah. So a lot of stuff kind of reverts to just like, well, let's break it into, that's sort of the n-gram thing. It's like, let's just break it into words and then pairs of words and triples of words and we'll get along with it. And you can get along with it. All right, let me set this up. So there's just some cost we don't need to worry about. If everything has that fixed cost, we don't have to worry about that. So there's just sort of this log piece. And so we can mess around, you don't have to worry about this, but you can change bases, the base of the logarithm. We can mess around with that a little bit. So we can turn it into a log E1 because we're happier with that. We can differentiate it. So we can say the cost is basically natural log of I plus 1. Right. And then plus 1, you might, maybe that doesn't matter too much, and we'll play around with that. We'll put an A in there as well. Okay, so the total cost is going to be this. We've got the cost of the ith word, and then the probability that it appears, right? So it's the expected value of the cost. So it's this object here. This is going to look a little bit like entropy, if you're familiar with entropy, but then in here this is log of I, right? So pi log pi. All right, so entropy, and I'll just throw it in. So it's measured. It's measure of information. It's an unfortunate use of the word information because I think it does connote meaning, and people get a little bit stuck on that, but it's much more of an engineering measure or physical measure. So entropy and uncertainty are nice variations on that. But this is, entropy is, this minus here really goes through here as log of 1 over pi. Yeah, von Neumann apparently suggested entropy because no one understands what that means. And anyway, but basically it's proportionally average number of bits that you would need to encode each word based on frequency of occurrence. So it's based on frequency, right? So the low frequency ones, more bits, high frequency ones, less bits. Right, so if you have something that appears half the time, then you'd need only 1 bit, and that's how this little structure would work. Something appears 64th of the time, then you could distinguish it with 6 bits. But of course, things are much rarer, certainly than a half. Like I said, maybe 1 in 25. So we can play around with this. We get rid of the log e and the log 2. We can mess around with that as well, and just have some constant times pi log base e. These are small details, and then this is the setup, right? So this is the thing. This is a good place to get to. The setup will be: we're going to minimize this. We're going to, well, depends how you want to do. We'll minimize this function. It's cost divided by entropy, and these are all the probabilities. There are n words. They all have these probabilities. We're actually trying to find the right set of probabilities for them, such that this is minimized. So it's a bit of a business. Of course, they have to add up to 1. So shorter words are cheaper. Longer words, have more information. So they're cheaper to send. They're low cost. These, of course, have more information, so they're valuable. You can easily just miss the word the in reading English, so it's gone. Okay, so that becomes the setup, and this is the horrible looking beast. So it's a Lagrange multiplier problem. You set up this big function, you say, okay, it's the thing we're trying to minimize or maximize. We add lambda times the constraint function, and I won't go into it too much, but this is basically the game. And we have these two pieces. We have C over H, right? So we're putting it is the cost. So it's going to be the sum of pi log of basically I plus 1. Very similar looking blob on the bottom. It's pi log pi though, which is the difference. And then the constraint function we can write in this way. It's the sum of pi minus 1, which we want to be 0. So what this does is you take a derivative of this thing, and what you're really saying is, you're living on this is some high dimensional space. There's a constraint, right? So this is where you have to be. This is the constraint. And then if there's some landscape under here, and it's got some contour lines, right? And so this is the function f. This is the constraint g, and these are lines of steepest descent or ascent. And what happens if we get the norm? What you want is the normal to the constraint, right? So the normal, you find the normal to the constraint everywhere. And then if you're kind of moving around, you're going up this hill. It's actually where the function is increasing in the same. It's increasing in the same direction as the constraint. That has to be the highest point. Right, so we have to be on this. This is our constraint. We have to be on this boundary somewhere, and so we can kind of wander around everywhere. But if we're like here, for example, if we're here. Here's the constraint, normal, and then this is the direction of increase. Actually, it's more like this. So these are not pointing in the same direction, and we'd say, okay, we could go up the hill. The hill is further up this way, and you get to the top of the hill here, or the bottom of the hill over here. That's Lagrange multipliers. You don't have to worry about it too much, but basically what happens is set this beast up here and then differentiate it with respect to p sub k, which does all of the partial derivatives. And we'll play around. There's some nefarious activities inside that, but I'll talk about it in office hours. So we're going to get through it. little Mandelbrot action. And Lagrange multipliers appear in a lot of different places, and it's nice to see them. It won't be the last time we see it. Okay. And I will make the course increasingly more interesting as we go along. All right. And that is the theory. Dinosaurs are very thin at one end and thick in the middle.